Section 1 Introduction. We've recently observed a significant shift in the field of large language models, LLMs. These models are now being enhanced to function as autonomous language agents, capable of performing tasks independently, rather than just responding to human queries. This trend has been demonstrated in several studies, including React, Toolformer, Hugging GPT, Generative Agents, Web GPT, Auto GPT, Baby Aggie, and LangChain. These studies have shown that it's possible to create autonomous decision-making agents by harnessing the power of LLMs. These agents use LLMs to generate text-based outputs and actions, which can then be used to make API calls and carry out operations within a specific environment. However, due to the vast scale and extensive parameter count of LLMs, the behavior of most existing language agents is not optimized or aligned with the reward functions of their environment. A recent exception to this is the language agent architecture known as Reflection, along with a few other related works like Self-Refine and Generative Agent. These models use a process called self-reflection, which involves verbal feedback, to help agents learn from their past mistakes. This feedback is converted into a textual summary and added to the prompt for the language agent, providing a clear direction for improvement and helping to prevent repeated errors. However, generating useful feedback from a pre-trained, frozen LLM is a challenging task. It requires the LLM to understand where the agent made mistakes and to generate a summary containing actionable insights for improvement. If the LLM hasn't been properly fine-tuned to specialize in these tasks, the verbal reinforcement won't be optimal. Moreover, existing language agents don't reason and plan in ways that are compatible with differentiable, gradient-based learning from rewards. This means they can't take full advantage of the wealth of reinforcement learning techniques available. To address these issues, we're introducing Retroformer in this paper. Retroformer is a framework designed to reinforce language agents by learning a plug-in retrospective model. This model refines the language agent prompts based on feedback from the environment through policy optimization. Our proposed agent architecture can learn from any reward information across multiple environments and tasks, and it can iteratively fine-tune a pre-trained language model. We've conducted experiments on open-source simulation and real-world environments, including Hotpot QA, which involves search-based question-answering tasks. Our results show that Retroformer agents learn faster and make better decisions than reflection agents, which don't use gradient for reasoning and planning. Specifically, Retroformer agents improve the success rate of search-based question-answering tasks in Hotpot QA by 18% in just 4 attempts. In summary, our contributions are as follows. 1. We introduce Retroformer, a framework that refines the prompts given to large language agents based on environmental feedback. This improves learning speed and task completion. We use a policy gradient approach, with the actor LLM being part of the environment, allowing learning from a wide range of reward signals for diverse tasks and environments. 2. Our method focuses on enhancing the retrospective model in the language agent architecture, without needing to access the actor LLM parameters or propagate gradients through it. This makes Retroformer a flexible plugin module for various types of cloud-based LLMs, such as GPT or Bard. Section Summary. The paper introduces Retroformer, a framework that improves the learning speed and task completion of large language agents by iteratively refining their prompts based on environmental feedback. This is achieved through a policy gradient approach, where the actor LLM is treated as part of the environment, allowing learning from diverse reward signals for different tasks and environments. Retroformer focuses on enhancing the retrospective model in the language agent architecture without accessing the actor LLM parameters or needing to propagate gradients through it, making it a flexible plugin module for various types of cloud-based LLMs. Section 2 Related Work. In this section, we'll discuss related work in the field of autonomous language agents, focusing on 5 key areas that are relevant to our research. We'll also highlight how our approach differs from these existing methods. Carrying out a complex task usually involves several steps. It's crucial for an agent to understand these steps and plan accordingly. The chain of thoughts, or COT, was a groundbreaking work that encouraged agents to break down difficult reasoning tasks into smaller, more manageable parts. Another approach, known as React, suggests using this reasoning and acting ability within language learning models, LLMs, to promote interaction with the environment. For example, it could involve using a Wikipedia search API. This is done by mapping observations to the creation of reasoning and action traces, or API calls, in natural language. This approach has led to the development of various applications, including Hugging GPT, Generative Agents, Web GPT, Auto GPT, Baby Aggie, and LangChain. However, these methods don't take advantage of valuable feedback, such as rewards from the environment, to improve the agent's behavior. As a result, their performance relies solely on the quality of the pre-trained LLM. Self-Refine addresses this issue by using a single LLM as a generator, refiner, and feedback provider. This allows for the iterative refinement of outputs. However, this method isn't specifically designed for real-world task-based interaction with the environment. RAP, on the other hand, repurposes the LLM to act as both a world model and a reasoning agent. It uses a strategy called Monte Carlo tree search for strategic exploration, taking into account rewards from the environment. This method allows for effective navigation and decision-making in complex domains. Recently, a framework called Reflection was introduced. This equips agents with dynamic memory and self-reflection capabilities, enhancing their reasoning skills. Self-reflection is crucial as it allows autonomous agents to iteratively refine past actions, make improvements, and avoid repeating mistakes. Section Summary. In the related work, we explore different approaches to autonomous language agents. Chain of thoughts, COT, decomposes reasoning tasks, while React encourages interaction with the environment. Hugging GPT, Web GPT, Auto GPT, Baby Aggie, and LangChain are applications of React, but they lack the ability to learn from feedback. Self-Refine allows iterative refinement of outputs, but it is not tailored for real-world task-based interaction. RAP repurposes the language model as a world model and reasoning agent, enabling effective navigation and decision-making. Reflection equips agents with dynamic memory and self-reflection capabilities to enhance their reasoning skills. Section. Transformer Reinforcement Learning. We're discussing the use of reinforcement learning, or RL, in fine-tuning language learning models, or LLMs. This process, often referred to as RLHF, has become a standard practice. It's been shown that RL is an effective way to guide LLMs towards desired behaviors that align with predefined reward functions. These functions can cover a range of areas, such as machine translation, summarization, and generating positive reviews. There are several popular RL methods used with transformer models. These include online RL algorithms like proximal policy optimization, PPO, and offline RL techniques such as implicit language queue learning, ILQL, and direct preference optimization, DPO. These methods have been used within the TRL/TRLX distributed training framework. However, using LLMs does present some challenges. While they're not designed for tool use or action taking, they've been found to work well in text-rich environments, especially when actions and states are accurately described using natural language. But there are still difficulties when applying LLM-based agents. One issue is that of spurious actions. LLMs aren't pre-trained or designed with an action agent application in mind. So, even if some restrictions are explicitly specified in the prompt, the LLM model may still generate actions that aren't in the defined action space. Another challenge is the limited prompt length. LLMs are stateless, but for applications, it's often preferred to give agents states or memories for better performance. It's been observed that LLM-based agents can easily fall into infinite loops if the states aren't managed properly. Many LLM agents concatenate all the previous state descriptions and actions into the prompt to give the LLM a state. However, this approach can lead to issues with prompt length. As the trajectory grows longer, the prompt runs out of space. Section Summary. Reinforcement learning, RL, has been widely used in fine-tuning language models, LLMs, to align their behaviors with predefined reward functions. Online RL algorithms like proximal policy optimization, PPO, and offline RL techniques such as implicit language queue learning, ILQL, and direct preference optimization, DPO, have been implemented in the TRL/TRLX training framework. However, there are still challenges in applying LLM-based agents, including the generation of spurious actions not in the action space and the limitation of prompt length, which can lead to infinite loops and prompt length issues. Section. Heuristic prompt engineering. Improving language model performance. Despite numerous strategies being put forward to enhance the performance of language learning model, LLM, agents, we still lack systematic methods for consistent model improvement. In reality, manual prompt tuning is still a common practice in many applications. Challenges in training. Most high-performing LLMs are too large to be accommodated on just one or two GPUs. It's technically difficult to optimize these LLMs directly, as is typically done in classical reinforcement learning scenarios. Notably, OpenAI hasn't provided any solutions for reinforcement learning-based fine-tuning. Many of these challenges arise because LLMs aren't pre-trained or designed with an action agent application in mind. Understanding the basics. Compared to LLM-based action agents, classical reinforcement learning agents, while not as adept at handling text-based environments in a zero-shot setting, can continually improve based on feedback and rewards from the environment. Well-known reinforcement learning algorithms include policy gradient, proximal policy optimization algorithm, PPO, trust region policy optimization, TRPO, and advantage actor-critic methods. Our proposed solution. In this draft, we propose a simple yet potent new framework to address the above challenges. On one hand, we aim to use classical reinforcement learning optimization algorithms, such as policy gradient, to enhance model performance. On the other hand, our framework avoids direct fine-tuning of the LLM. The crux of our approach is to train a retrospective language model, LM, rather than directly training the LLM. This retrospective LM takes user prompts, rewards, and environmental feedback as input. Its output serves as a prompt for the actual LLM. We use reinforcement learning algorithms to optimize the weights in the retrospective LM model, not directly on the LLM. In our framework, the weights in the actual LLM are assumed to be fixed, untrainable, which is suitable for scenarios where the LLM is either too large to tune or tuning is not allowed. Another way to view our framework is that we train a retrospective LM to automatically tune prompts for the LLM agents. In this case, reinforcement learning algorithms like policy gradients are used to optimize the prompts. Ideally, the retrospective LM can help condense past experiences, user prompts, and environmental feedback into a concise text with a length limit, making it easier for the LLM to process. To a certain extent, in our setup, the original LLM can be considered part of the environment since all its parameters are fixed. Section summary. The lack of systematic methodologies for consistent model refinement in language model agents, LLMs, has led to the continued use of manual prompt tuning in many application scenarios. Additionally, optimizing LLMs directly is challenging due to their large size and the absence of pre-training or design. For action agent applications. To address these challenges, we propose a framework that leverages classical reinforcement learning (RL) algorithms to optimize a retrospective language model (LM) instead of the LLM itself. This allows for automatic prompt tuning and improves the LLM's performance by summarizing past experiences, user prompts, and environment feedback into condensed text for easier digestion. Section 5. Notation and Formulation. In this section, we're going to explain the notation and formulation of a large language model, LLM-based agent. Think of the LLM-based agent as a function that takes prompts and produces actions. The prompts can be either the ones given by users or some contextual information. The context here is a representation of the current state provided by the environment. The actions are the responses generated by the agent. It's important to note that these actions are usually generated in a random manner, hence the function is random. The randomness is represented by a subscript in the function. Interestingly, the LLM-based agent doesn't have a state of its own. All the states and possible memory are represented as text in the prompt. The environment in which the agent operates is defined by a state transition function and a reward function. The state transition function takes a state and an action and produces a new state. We assume that both states and actions are represented as text. The randomness in the state transition is also represented by a subscript. For each state, a reward function is defined that assigns a reward to that state. At each step, the state is described using natural language and integrated into the context. Previous states may also be described and embedded in the context to help the agent make a good guess about the next action. The ultimate goal, as in all reinforcement learning settings, is to maximize the cumulative rewards. In many cases, the rewards are sparse, meaning that most states have a reward of 0, with only a few exceptions. The retrospective model takes all the previous states, actions, rewards, and the user prompt as input, and transforms this information into a new prompt for the LLM agent. This model has its own randomness and a set of learnable parameters. The goal of the reinforcement learning optimization is to find the parameters that maximize the sum of the rewards, subject to the state transition function. It's important to note that the only learnable parameters are in the retrospective model. Since the LLM agent model is fixed, it can be considered as a part of the environment. If we construct another environment with the same reward function and a modified transition function that includes the LLM agent, then the objective is just a regular reinforcement learning optimization, and all the popular reinforcement learning algorithms apply. Section summary. In this section, the notation and formulation of a large language model, LLM-based agent are described. The LLM agent is a function that takes prompts and contextual information as input and outputs actions. The agent's actions are sampled auto-repressively, and it is stateless, with all states and possible memorization characterized as text in the prompt. The environment is defined as a state transition function and a reward function, where states and actions are represented using text. The goal is to maximize cumulative rewards, which are often sparse. A retrospective model is introduced to massage previous states, actions, rewards, and user prompts into a new prompt for the LLM agent. The RL optimization objective is to maximize the expected sum of rewards over time. Section 6. Our approach, reinforcing retrospective language agent. We're introducing our approach, which we call the Retroformer, a system designed to enhance the performance of language models. The Retroformer consists of two main parts, an actor language model, which we'll refer to as M_A, and a retrospective language model, referred to as M_R. The actor model, M_A, is responsible for generating thoughts and actions. It's a fixed model, meaning its parameters can't be changed. Examples of such models include GPT and BARD. On the other hand, the retrospective model, M_R, provides feedback to the actor model to help it improve. This model is smaller and can be fine-tuned, even when resources are limited. The Retroformer also includes a step for policy gradient optimization. This step is designed to strengthen the retrospective model using a gradient-based approach. Now, let's delve into the architecture of the Retroformer. We use a standard communication protocol, adapted from the Relexion agent architecture, for the actor and retrospective models. The retrospective model helps the actor model improve by adding feedback to the actor's prompt. The actor model is a language model that resides in the cloud. Its parameters are hidden and can't be changed. It generates actions based on the states it observes. We select an action, which we'll call _T, from the current policy at a given time step, T. We then receive an observation, S_T, from the environment. We use React as our actor prompt. The retrospective model, M_R, is a local language model. Its main job is to generate self-reflections, which provide valuable feedback for understanding why previous failure occurred and how to avoid it in the future. The model operates under a sparse reward signal, such as binary success status, success, failure. It identifies the root cause of failure by considering the current trajectory and its persistent memory. The feedback from the retrospective model is added to the actor's prompt to help avoid repeating the same mistakes in the future. For example, let's say the agent failed a multi-step task in a previous attempt. The retrospective model can identify that a specific action, _T, led to subsequent mistakes and ultimately to failure. In future attempts, the actor model can use these self-reflections, which are added to the prompt, to adjust its reasoning and actions at time t, choosing a different action, _T prime. This iterative process allows the agent to learn from past experiences within a specific environment and task, thereby avoiding repetitive errors. Section summary. The proposed framework, Retroformer, consists of two language model components, an actor model that generates reasoning thoughts and actions, and a retrospective model that generates verbal reinforcement cues to assist the actor in self-improvement. The actor model is a frozen language model with inaccessible parameters, while the retrospective model is a smaller, local language model that can be fine-tuned. The collaborative functioning of these modules allows the actor to adapt its reasoning and actions based on self-reflections, preventing repetitive errors in future attempts. Section: Memory Module. The Memory Module section discusses how the actor model generates thoughts and actions based on its recent interactions, which are considered short-term memory, and reflection responses, which are considered long-term memory. Short-term memory. This is represented by the trajectory. History of the current episode, which aids in decision-making and reasoning. Long-term memory. This is made up of reflection responses that summarize previous unsuccessful attempts. These are added to the actor prompt as long-term memory. To help optimize the policy, we store the prompts and responses of the retrospective model of each trial, along with the episode returns, in a local dataset known as the replay buffer. We then sample from this replay buffer to reinforce the retrospective model at the end of each episode. The long and short-term memory components provide task-specific context over several failed trials, while the replay buffer provides examples of successful reflections across tasks and environments. This allows our Retroformer agent to not only learn from failed trials in the current task but also to explore and learn from successful reflections in other tasks. Replay buffer. This is the memory that stores the triplets of the reflection prompt, reflection response, and episode return of each trial and task. In terms of reward shaping, we apply this to the binary rewards to gather more information. For question answering tasks, we use an F1 score grading system to evaluate the alignment of the generated output with the expected answer, which serves as the reward function. In the policy gradient optimization section, the actor model is seen as a frozen language model, like GPT, with inaccessible model parameters. In this case, the best way to improve actor performance in a given environment is by refining the actor language model's prompt. As a result, the retrospective model, a smaller local language model, rephrases the actor's prompt by including a brief summary of errors and valuable insights from failed attempts. Our goal is to optimize the retrospective model using environment reward. The desired behavior of the retrospective model is to enhance the actor model in future attempts. Therefore, the difference in episode returns between two consecutive trials serves as a reward signal for iteratively fine-tuning the retrospective model. This acts as a surrogate for reinforcement learning aided by gradient-based signals. The specifics of this approach are outlined as follows. Section summary. The actor model uses short-term memory, which is the trajectory history of the current episode, and long-term memory, which includes reflection responses from prior failed attempts. These memories are stored in a replay buffer, which contains instruction response pairs and episode returns. The replay buffer allows the agent to learn from both failed trials in the current task and successful reflections in other tasks. Additionally, reward shaping is applied to enhance the actor's performance, and the retrospective model is optimized using the difference in episode returns as a reward signal. Section: Instruction and Response Generation. In the section titled Instruction and Response Generation, the authors discuss how their retrospective model works. At the end of each trial in a given environment, the model generates a pair of instructions and responses. The actor interacts with the environment to create a trajectory, which is then evaluated and given a score. This score is used to provide verbal feedback to refine the actor's prompt. The instructions and responses from all trials are stored in a dataset, referred to as the replay buffer, which is used to fine-tune the model at the end of each episode. The authors then discuss the reflection response rating. They explain that the retrospective model generates a response that summarizes the mistakes made in a trial, which then influences the return in the next attempt. The authors note that any differences in returns are due to the reflection responses. Positive differences indicate better responses that help the actor learn from previous errors and should be rated higher. Negative or zero differences indicate worse responses that should be avoided and rated lower. The authors define the rating score of a reflection instruction response pair as the difference between the returns of two consecutive attempts. The authors then move on to discuss proximal policy optimization. They explain that the optimization step of their model, called Retroformer, is an iterative process. They use the differences in episode returns as the ratings for the generated reflection responses. The retrospective language model is fine-tuned at the end of each episode using standard training procedures with proximal policy optimization. The authors note that the actor, retrospective model, and the policy gradient optimization module work together in a loop until the environment deems the trajectory to be correct. In practice, the authors use offline reinforcement learning methods instead of online. Optimization. They collect a dataset by rolling out a base policy, which includes the actor in the retrospective model, in the tasks in the training sets for a certain number of trials and compute the ratings. They then fine-tune the retrospective model offline before evaluating the agent in the validation tasks. During online execution, they use a method called best of n sampler, with the scores evaluated by the learned reward model, as an alternative method of generating better retrospective responses in each trial. Section summary. The retrospective model generates instruction response pairs by interacting with the environment. These pairs are stored in a replay buffer and used to fine-tune the model. The rating score of each pair is determined by the difference in returns between consecutive attempts. The optimization process involves using these ratings to train the model through proximal policy optimization. Offline RL methods are used to collect the dataset and fine-tune the model before evaluating it on validation tasks. Section 7 Experiments. We've carried out a series of comprehensive experiments to assess the effectiveness of our approach. This includes comparing our method with React and Reflection, as well as examining and discussing the text and actions generated by the agent. We've used the open-source Hotpot QA environment for our experiments. This environment is designed for search-based question-answering tasks, which allows us to test the agent's ability to use tools in a large state action space. In the Hotpot QA environment, the agent is tasked with answering a question by searching through Wikipedia pages. The agent has 3 possible actions or API calls at each step. 1. Search entity. This action involves searching for a specific entity on Wikipedia. If the entity exists, the agent returns the first paragraph. If it doesn't, the agent suggests similar entities to search for. 2. Lookup, keyword. This action returns the next sentence that contains a specific keyword in the last passage found by the search action. 3. Finish, answer. This action provides the answer and completes the task. For our dataset, we gathered 3,383 reflection samples by running the base rollout policy for 3 trials, n equals 3, for 3,000 tasks in the training set. Out of these, 1,084 instruction response pairs received positive ratings. We used GPT-3 model, Text DaVinci 003, as the frozen actor model. For the retrospective model, we used LongChat model, LONGCHAT7B-16K, a language model with a context length of 16K, fine-tuned on instruction following samples from shared GPT. In all our experiments, we set the temperature of the actor language model to 0, T equals 0, and top P to 1. This was done to separate the randomness of the language model from the effects of reflections. We recognize that a higher temperature value could promote exploration, but it could also make it harder to compare our results with existing baselines that use T equals 0. Our learning framework was built using several open-source tools. We used OpenAI connectors from LangChain to construct our actor models M_A. During the inference of the retrospective model, we hosted an API server using fast chat and integrated it with LangChain agents. This tool can host LONGCHAT7B-16K with concurrent requests to speed up RL policy rollouts. For fine-tuning the retrospective model, we developed our training pipeline with TRL, which supports transformer reinforcement learning with a PPO trainer. We provide the details of the specific prompts we used and the full agent demonstrations and examples for each environment in the following sections. Section Summary. The experiments conducted in this section evaluate the proposed method by comparing it with React and reflection performances. The evaluation is done using the Hotpot QA environment, which consists of search-based question-answering tasks. The agent is asked to solve these tasks by searching in Wikipedia pages and choosing from 3 action types: search, lookup, and finish. The dataset used for training consists of 3,383 reflection samples, and GPT-3 is used as the frozen actor model. The learning framework is developed using multiple open-source tools, including LangChain, FastChat, and TRL. Section: Training. We've refined our retrospective model, which we'll call M_R, using a method known as 4-bit quantized LoRa adapters, where R equals 1. This was done on offline reinforcement learning datasets, with 4 epochs, a batch size of 8, and a learning rate of 1.4 times 10 to the power of -5. The model has about 530,000 trainable parameters, which is only 0.015% of the total parameters in the Llama 7B model. Initially, we used a supervised fine-tuning trainer on samples that received positive ratings for 2 epochs. After that, we implemented the RLHF pipeline, which includes reward modeling and reinforcement learning fine-tuning with PPO. This was done on the entire offline rating dataset using the default settings for the Llama 7B model. We evaluated our model based on the success rate and the average returns per episode over validation tasks in a given environment. We tested the agent on 100 validation tasks from the distractor development split of the open-source Hotpot QA dataset. We compared our model with 2 language agent baselines. The first one is React, which is the foundation for the Auto GPT model. However, this agent doesn't learn from environmental rewards, so it serves as a baseline to show how the actor model performs without exploration and exploitation in the environment. The second one is Reflection, a state-of-the-art language agent architecture. This agent learns from verbal feedback from the environment but doesn't explicitly use gradient signals. It serves as a baseline to show the effectiveness of gradient-based learning for reasoning and planning. When we compared our Retroformer with these baselines, we found that our model consistently improved agent performance over trials, especially in the early ones. This is because early exploration benefits the exploration of the state action space. Our agent also outperformed the 2 strong baselines. Specifically, our reinforced model provided better reflection responses in the early trials, enabling the agents to learn faster and perform better in the end. Our Retroformer agent achieved a success rate of 53% in 5 trials, which is better than the state-of-the-art 50% success rate reported by a much larger language model, GPT-3, used as the retrospective component. These results demonstrate the effectiveness of our policy gradient approach for fine-tuning the agent with offline samples. Section Summary. The authors fine-tuned the retrospective model using 4-bit quantized LoRa adapters on offline RL datasets, achieving a success rate of 53% in 5 trials, outperforming state-of-the-art baselines. The results demonstrate the effectiveness of their policy gradient approach for fine-tuning the agent with offline samples. Section 7.4 Discussion of the reinforced agent behaviors. We're going to delve into how the retrospective model, denoted as M_R, is enhanced through policy optimization. We'll do this by comparing the responses generated by the unaltered retrospective language model, LM, and those produced by the fine-tuned, reinforced LM. We've noticed two main behaviors that the fine-tuned LM learns through a process of trial and error. These two behaviors, reinforced through learning, help the agents perform better than the baseline models. Firstly, let's talk about the precise credit assignment for failed trials. We've provided an example that demonstrates why the reinforced responses are better at analyzing the mistakes made in previous failed attempts, and how they help the agent avoid repeating the same errors. In the last attempt, the agent failed primarily because it considered both Teen Titans and Teen Titans Go as answers to the Teen Titans spin-off series, when the correct answer should only be Teen Titans Go. The agent lost sight of its original goal amidst a series of thoughts, actions, and lengthy observations. The reflection response from the unaltered model tends to use a lot of should have phrases and, while it's linguistically fluent, it simply repeats the previous sequence of actions that led to failure. This encourages the agent to repeat these steps in the next attempt, creating a never-ending cycle. In contrast, our reinforced response encourages the agent to focus on the spin-off series right from the start. It instructs the agent to find the answer in its previous actions and observations, with a particular emphasis on the search results for Tara Strong. In short, our proposed reinforcement learning approach offers better credit assignment and root cause analysis capabilities. It can provide practical suggestions for the next attempt. Secondly, we've noticed structured reflections and action plans as an emergent behavior of the reinforced model. It can automatically rephrase the original responses into two distinct structured sections, namely the reflection section and the new plan section, even though it wasn't explicitly trained or prompted to do so. An example of this is shown in the paper. The rephrased response reflects on the past in the first paragraph and provides actionable insights in the next, whereas the response from the unaltered LM mixes both parts in one paragraph, making it difficult to understand. We've also noticed that the reinforced response removes the cluttered, irrelevant, next trial content at the end for a cleaner format, which is likely a result of language model hallucination. Section summary. The fine-tuned, reinforced language model, LM, outperforms the frozen LM by learning two reinforced behaviors through trial and error. These behaviors help the agents prevent repetitive errors and provide actionable insights for future attempts. Additionally, the reinforced model automatically paraphrases responses into structured sections, improving comprehension and removing irrelevant content.